Okay, so we're going to look at some review questions for rate in mechanical systems. That's going to include our linear rate, just basic velocity and acceleration. That's also going to include our rotational systems, which would be angular velocity or angular acceleration. So you might want to look up these equations for this review guide because you'll have to write them down later. Okay, so some vocabulary words, you can look these up. A vector is just a quantity with a size and a direction. A scalar would just be a size. A rate is going to be some counted object or how many things divided by the time. So we could say that a rate would be what is done or amount of objects processed. Okay, or how far I went. This is all over a time, so how long it takes me to do something. Okay, linear displacement, that would be how far you are from the starting point. So remember the example that we used here would be the person going around the track. Okay, so if they arrived back at their starting point, then their displacement is going to be 0 meters. But then if we look at the distance here, the distance would be how far around the entire track. So if we were saying a 400-meter track, then my distance would be 400 meters. So displacement is how far from some reference point, and distance is just total distance traveled. We don't care about any reference points. Okay? Angular displacement, that's the angle that an object travels through. We're looking for radians, so the radian measurement an object travels through from its starting point. And this will never be 0 unless the object doesn't go anywhere. Okay? Average speed is total distance over total time. So that gives you an average speed for the scenario. And speed is just distance over time. Velocity compared to speed, velocity is going to have a direction. So this is going to be displacement over time. Okay, so this is how fast something is traveling with respect to its direction. Speed is a scalar quantity. So speed, it does not care about the direction, but velocity does. So this is a vector quantity. Okay, position time graphs, that's just a graph that shows the position with respect to the time. So time is on the bottom, that's the independent. Position is on the vertical or the dependent axis there. And velocity time graphs have time down here again and velocity here. So position time graphs can tell me how far something goes. I can know the distance. Or if I were given something like that, I can calculate the slope of this, because the slope of this is going to tell me speed or velocity. Okay, if I wanted to know the velocity, then this would be positive, so I just have to say it's going away from the center or away from the position, starting position. All right, if we look at velocity time graphs, our slope here tells us acceleration, because we can find the slope of this line where you'd have a velocity here and a velocity here, find the slope between those 2 points, and we're going to have acceleration. Okay, and acceleration is the change in velocity. Okay, so these are pretty quick definitions for these words here. Make sure that you are complete with your answers. And deceleration would be a change in velocity. This would be a negative change in velocity, so this would be slowing down. So these are pretty small snapshots of what these words are, so make sure that you look them up completely. So conceptual questions here, again, I'm just going to kind of give snapshots for the answers here. I'll be looking for more complete answers. You'll probably want to look up a little bit more than what I'm going to tell you just to review on these. All right, so name a few systems where it would be important for a technician to understand how to control mechanical rate. That could be either linear or angular rate. So the big one here, a lot of people looked up and answered in their bell ringer questions, are cars. Okay, so this could be anything from the wheels to the flywheel to the motor in general. There's lots of gears and things moving on a car, so you're going to want to understand how the rate works in that vehicle. Okay, another scenario may be in a factory, so maybe a robotic arm. All right, so something that's going to move, something in a factory, so industrial applications, you would want to understand how fast things are moving in a factory because you don't want to make it dangerous for people and you want to make things move efficiently. Okay? And then let's think of a third one here. Might be, let's say, a theme park ride. So this would be like the swing in the example I gave in the notes. Okay? So all three of these, remember when we're answering questions like this, we don't want answers like, so it don't break. We don't want answers like that. That's too general, not specific enough, and it doesn't tell me anything about mechanical rate. So when you give explanations for how these systems involve mechanical rate, think about the equations. So the car could be distance over time, or it could be velocity over time, where we're looking at a velocity or acceleration. So how far it went over how much time it took to get there. So that could be, they want to understand how fast a car goes from 0 to 60 and why it goes as fast as it does. Robotic arm, this is probably going to be distance over time as well. So you don't want that robotic arm going too fast because it could ruin the thing that it has a hold of, or it could not be able to keep up with the rest of the people or the machines. And a theme park would obviously be, you don't want the rides going too fast because it could endanger the people that are on the ride. Okay, so general equation for rate in a mechanical system, you could look that up. We talked about that in the last slide. All right, so for number 4, it says the rate at which a car moves is described as 35 miles per hour northeast. Explain the difference between scalar quantities and vector quantities with this information. So remember, scalar quantities, that would be just a regular size value. So this could be 35 miles per hour. And then the vector quantity, I have to have a size and a direction. So this is going to include that 35 miles per hour northeast. All right, so the difference between those two is a vector quantity is going to be more descriptive because it has that direction. So for number 5, positive and negative acceleration, that would go back to your last page as well. So positive acceleration is going to be increasing velocity or increasing speed, and negative acceleration would be decreasing speed, which this is called deceleration, which is essentially just slowing down. So I'm coming to a stop or something like that. I'm just coasting and I'm letting friction or drag slow me down. So that would be deceleration. So number 6, you can refer to a worksheet that we talked about for that one. We're going to kind of jump down here to number 7 and 8 looking at these two graphs. So motions for 5 objects, A, B, C, D, E, are represented by lines on a position time graph. For A, we want to write the letters for the objects that have the greatest constant velocity, and we're going to consider absolute value only, so that means forget about positive and negative, it could be either one. So we want to find the greatest constant velocity. So remember, for position time graph, so we're looking at a position time graph on this one, it's not a velocity time graph, make sure you're paying attention to that. The greatest slope is going to have the greatest constant velocity. So B would look like a pretty good slope, and E would look like a pretty good slope. So those would be the steepest slopes. Now there aren't any numbers on here, so it's kind of hard to tell exactly how fast they're going. If you had a ruler or something, you could draw a flat line and then measure how far we are from the flat line and then compare it to that one. But B and E would be the two that have the greatest constant velocity. So for the next one, write out the letter for the object that has the least constant velocity. So it has to have some kind of a velocity. So I'm going to rule out A because this person is not moving. They're just staying in one place. So their velocity is essentially 0, which means they don't really have a velocity. So we're going to look at D here. So C is, again, that's another person at rest or another object at rest. So D right here, if I compare those, it has some velocity, but it's not as steep as B and E. So D is going to be the one with the least velocity. Okay? And then, again, for C here, I just mentioned this already. A is at rest and C is at rest because they have a flat line. There is no slope, so that means there's no velocity. So another position time graph here, but we're going to be more specific because we have actual values on our grids here, or our plane. So we're going to find the velocity of this object and then the position after 3 seconds. So how do we find velocity of a position time graph? I mentioned this earlier in the video, but we need to find the slope of the object. Okay, and this one is pretty straightforward. We can start from 0, 0, and we can end at 5, 10, or that means we went 5 seconds and 10 meters. So what you want to do here is count. You could do the slope formula if you wanted to. So that's y2 minus y1 over x2 minus x1. But I think it's a lot easier for this scenario just to count up and over, because it's also rise over run. Right? Slope is rise over run. So this person went 10 meters, so that would be the rise in 5 seconds. So that's the run. So if we do 10 divided by 5, then that velocity is going to be 2 meters per second. So we just simply do 10 divided by 5, and we get a velocity of 2 meters per second. Okay, so for B here, if we're trying to find a position after 3 seconds, well, we just want to go to 3 seconds and then see where that lines up on my graph. Okay, so 3 seconds is here, and then we're going to kind of look over here to see where that lines up. So my lines aren't perfectly drawn here, but it's going to be 6 meters. Okay, and we know that just by looking at this as well. If we know we're going 2 meters per second, well, after 3 seconds we went 2, 4, 6 meters. So the position is 6 meters from the start, or they just went 6 meters. So now we're looking at a velocity time graph. So given by the words velocity and time, we have to kind of change our brains a little bit, because this is how fast objects are going now, and our slope represents acceleration. So if we just kind of pick this out here, we have A, B, C, and F. If those were position time, if this were a position time graph, those would be at rest. But now A, B, C, and F, those would be considered constant velocities. So they're moving at a constant speed. Okay, so this would be a negative acceleration, or slowing down, and then this would be going backwards. Okay, because this is 0. If we're going from, say, some value 2 meters per second squared acceleration or velocity to 0 velocity to negative velocity, then this would be switching directions, because I'm going back to my starting point and then I'm going beyond that. All right, so let's answer these questions on the left. Write the letter for the object that has the greatest constant acceleration. So that would mean we're going to forget about positive and negative here again. We're going to look at slopes. So the one that has the greatest acceleration, or positive slope, would be letter E. Okay, it's still a negative velocity, but this is increasing speed, so that would be a positive acceleration. Objects that have constant velocity, we talked about that already, so that's going to be A, B, C, and F. Constant velocity is just going to be a flat line. Okay, so an object that is at rest, and we could kind of go back on our answer here with C, but C is at rest because it's traveling 0 meters per second. Its velocity is 0 there. So I would still say that this is, well, so I would say that we could take C out of this one, because technically it doesn't have any velocity because it's going 0 meters per second. So C would go here. And then for question D, write out the letter for the object that has constant deceleration. So as I mentioned here, this is going down, so it's slowing down, and that has a deceleration because the slope is negative. Okay, so let's scroll down here, and we can kind of pick out some of these. I'm going to jump to my formula down here to make sure that we have the correct equations written down. So my equation for distance here, I'm going to write out my speed equation. So speed equals distance over time. We're going to rearrange this here to figure out our distance traveled. So we're going to multiply by t, and we'll get distance equals speed times time. And our units for distance would be meters. We could also have miles. Depending on what we're looking for, we could have feet. All right, it's some kind of a measurement unit. So velocity is going to be velocity equals displacement over time. So this is a little more specific because we have that value for displacement. So remember, displacement is going to be final position minus initial position. And our value for velocity, a lot of the times we use meters per second. Maybe we've used miles per hour if we're talking about English terms. But most of the time we're doing meters per second. So acceleration, that's going to be change in velocity over time. And again, we need to know what change in velocity is. That's going to be final velocity minus initial velocity. And our units for this are going to be meters per second squared. And I would say most of the time this is what we've used, because we haven't used any square units here, but we could maybe say feet per second squared or miles per second squared. It's going to have a square unit in the bottom, because remember, this is change in velocity. So it's how much my velocity, which would be meters per second, is changing over a time. So it's meters per second, which is meters per second squared. Okay, now these three relate to these three, but these answers, or these equations here, come from our angular equations. So we're going to take our angular equations and change them into linear equations. That's what we're looking to do for this table. So the angular displacement, that's just going to be delta theta, which is going to be your, it's usually 0 for your initial, but it's going to be your final angle minus your initial placement or angle. Okay, and our units here are going to be radians. And occasionally we could use revolutions depending on what the answer is supposed to be. Angular velocity, that's the omega symbol, is going to be delta theta over time. And remember, delta theta we can look at the last table for. And our units for this will be radians per second, or usually it's radians per second. It can also be revolutions per minute. Most of the time we're looking for those. All right. Now the third one here, is going to be angular acceleration. So that is alpha, and that is change in angular velocity over time. So this is change in angular velocity is going to be final angular velocity minus initial angular velocity. And similar to these units, or these ones up here, it's going to be radians per second squared. And it might be revolution per minute squared. And I should have wrote MIN here. But most of the time, we're going to be using a radians per second again. So these last three are just taking our angular equations and turning them into linear equations. So the thing that makes the difference here is the radius of the object, or how far out from the center of motion that we're looking. So to find a linear distance here, we just need to use that radius here. So let's say x, or delta x, is just going to be radius times my change in angle. And really, when we talk about radians, this is how we get from angles to radians and such. We have to use that radius, the definition of a radian. So if we want to go from angular velocity to linear velocity, that would just be v. We're going to take the radius times the angular velocity. So if we want to get to linear acceleration, that's going to be a equals radius times angular acceleration, which is alpha. Okay, so our units here would just be the same as the ones above. So meters, miles, and maybe feet, depending on what we're looking at. Linear velocities, meters per second or miles per hour. And linear acceleration is going to be meters per second squared most of the time. So I would have those equations handy from the last table there. We're going to be using those for these questions, and these are the ones that require some work shown. Okay, so starting out, a box sitting on a conveyor belt moves the distance of 88 feet in 8 seconds. What's the speed of the conveyor belt? So the equation for speed is distance over time. And we have a distance of 88 feet and a time of 8 seconds. So it might be helpful to underline information in the equation. So let's just plug this in. So we are going 88 feet over 8 seconds. And we can divide those two. 88 divided by 8 gives us 11 feet per second. So that would be our speed here. So the second one, the deposit cylinder. So So that's the thing that goes in the little air vent at a drive-through window. Travels at a constant speed of 2 meters per second, and it takes 21 seconds to travel from the depositor to the teller. What distance did the cylinder move through? So again, we're using speed equals distance over time, and maybe you want to solve this for distance, so it'd be distance equals speed times time. So we can use this for our equation. So the speed is 2 meters per second, so maybe we're going to write those down as well, 2 meters per second, and our time is 21 seconds. So we just plug those into our equation here, 2 meters per second times 21 seconds, and we're going to get a nice answer of 42 meters. So that's how far that little cylinder moves to get back to the depositor to the teller. And we want to look at some dimensional analysis here to make sure that we have the correct units. If we have meters per second times seconds, those are going to cancel out, right? Because this is in a denominator and that's in a numerator, so we have meters on the top. So for number 14, we're looking at a car. So a dragster can start from rest. That's an important word. That's 0 meters per second. So maybe underline whenever you see rest or stop. And reach a speed of 250 miles per hour, which is 367 feet per second, in 5.5 seconds. What's the acceleration of the dragster in this amount of time? Now, we have a couple different units for speed here. We have miles per hour and feet per second. So we have to make sure that we use the one that lines up with our time, which is seconds. So we want to use this 367 feet per second and forget about the miles per hour. Now there will be times where you're going to have to convert that, but this is nice because it's already given the conversion or the converted number to you. Okay? So we're looking for acceleration. So we have to know the acceleration equation. Acceleration is change in velocity over time. And I would rather write this equation down, acceleration, so my change in velocity is final minus initial over time. And then this gives me a better equation to plug all my variables into. Okay, so my initial velocity, I'm starting from rest, that's 0 meters per second. And then I'm getting up to a final speed of 367 feet per second. And I should have written this as feet per second. I guess I'm just in the habit of writing meters per second. So I'm going from 0 to 367 in a time of 5.5 seconds. So now we can plug all those into our equation. So acceleration equals my final, so 367 feet per second minus 0 feet per second over the time of 5.5 seconds. All right, so simplify this down a little bit. It's going to be 367 feet per second over 5.5 seconds. And put that in our calculator and get an answer. So the acceleration of this car is going to be 66.73 feet per second squared. So pay attention to the label here for our answer. Remember, it's always second squared because it's change in velocity over time. So that time unit is always going to be squared. So the dragster in the previous problem opens up a drag parachute. So that's the little parachute that flies out behind the car after the quarter-mile track is complete in order to slow the car. So the dragster decelerates from 367 feet per second to a final speed of 67 feet per second. And so we need these numbers. Okay, and forget about that because remember, we don't need miles per hour. In 20 seconds, so I have time value there. So what's the deceleration of the dragster during the 20-second time period? So now our initial velocity is going to be that 367 feet per second because we're slowing down. So we want to see our acceleration or our deceleration here going from that to that. So the final velocity is 67 feet per second. And then our time value here, it takes us 20 seconds to slow down. So let's plug that into our acceleration equation. So final is 67. Initial is 367. And then our time is 20 seconds. So let's simplify this down a little bit. So 67 minus 367, that's negative 300 feet per second over 20 seconds. And then we put that in our calculator if you need to. but that's going to give us a negative 15 feet per second squared. So that is our deceleration when that dragster slowing down. So down here is an example that we did in class one time. We're looking at a scanner dish of a weather radar antenna system. So it's going to complete 160 revolutions in 1 hour. And we're looking for the angular speed of the scanner dish. And we're looking for it in revolutions per minute, that's part A, and radians per second, that's part B. Okay, so we have to do a little bit of conversion here to get these answers correct. So our equation, remember, for angular acceleration, or not, so our equation for angular speed, that's what we're looking at. That's omega equals change in angle, or radians, over time. This can also be in revolutions, okay, but our time here we have to have it in minutes. So that's radians, or that's revolution per minute. So we can keep those revolutions, so 160 revolutions, but we're going to have to change the 1 hour. So this is our time value, and this is our displacement value. So 1 hour is 60 minutes, right? So then we can just do 160 divided by 60 to get our revolutions per minute, which is 2.67 revolutions in 1 minute. So that antenna goes a speed of 2.67 revolutions per minute. So for the next one here, we're using the same equation here, or we can just kind of take our answer that we had there, which is probably the better option, and we're going to change that to radians per second. So this will be a conversion type problem. So we have 2.67 revolutions in 1 minute, and we want to set up our tracks here and convert. So the minutes are the easier ones to start with. So there are 60 seconds in 1 minute. So our 1 minute goes there, and 60 seconds goes there. So that way our minutes cancel out. And then we want to take care of the revolutions. So my revolutions are going to go on the bottom. So 1 revolution, we're turning that into radians. So remember, 1 revolution is 2 pi radians. And then that will cancel out our revolutions. So our final will have radians per second. So we'll need to take 2.67 times 2 pi divided by 60 to get our answer in revolutions per, or to get our answer in radians per second. Which is 0.28 radians per second. Okay, come on. 0.28 radians per second. So let's look at the last one here. We're looking at angular acceleration. So we have an electric motor shaft under load, starts from rest. So remember, that's an important word to underline, and reaches its designing operation speed, or design operating speed, of 1,040 revolutions per minute. And reaches its design operating speed of 1,040 revolutions per minute. So that's another important piece. In 3.6 seconds after the motor started. What's the angular acceleration of the electric motor in radians per second squared? So we have to make sure that everything is in radians per second before we use our equation. But our acceleration equation, so angular acceleration is going to be change in angular velocity over time. And again, I would write the better equation for plugging things into. So that would be my final angular velocity minus my initial angular velocity over time. And we're going to write out all of our variables. So initially, we're starting from rest. So that's 0 radians per second. And then the final angular velocity. And then the final angular velocity is 1,040 revolutions per minute. So we're going to have to change that. Our time is 3.6 seconds. So let's convert this to radians per second in order for us to use it. So we have 1,040 revolutions in 1 minute. Okay, so 1 minute goes up here, and 60 seconds on the bottom. That way we can cancel out the minutes. And then revolutions goes down here. So 1 revolution is equal to 2 pi radians. So this is just like the last problem that we did. And we're going to have to do 1040 times 2 pi, and we're going to have to divide that by 60 to get 108.91. So we'll just write it over here, 108.91 radians per second. Now we can use that number. So we don't want this one anymore. We can use this number in our equation. So we have final, which is 108.91 radians per second, minus initial, which is 0 radians per second, over that time value of 3.6 seconds. And that is our angular acceleration that we're looking at here. So it's just going to be 108.91 divided by 3.6, which would be 30.25. And then our units for angular acceleration are radians per second squared. All right? So hopefully these review problems help you out, help you study for a quiz or a test or something like that. But let me know if you have any questions on these and I can help you out a little bit more. Thanks for watching.